So we're going to do tangent planes and normal lines today. And as I mentioned on day one, Calc 3 is kind of a redo of Calc 1, but we do it in 3D. So I want you to recall back in your Calculus 1 days when you were studying graph of a function, say this. Do you remember when they asked you to find tangent lines? Do you remember this at all?
Yes.
I hope so. That's because that's one of the key things. You know, they'll pick a point on your graph and they'll go, okay, that's when x is equal to c, say, and then they'll draw a tangent line like this, and then they'll say, what is the equation of your tangent line? Does this ring a bell at all for you from Calculus 1 days?
Y equals mx plus b.
True, true, very good. And what is m?
The slope.
So
True, that's from algebra, but more specifically, what's the slope?
The derivative?
Yeah, that the slope would be your derivative of the function evaluated at c. Does everybody remember this?
Yes.
Okay, I hope so, because we're going to do that in 3D. Well, what do you mean? Well, in 3D, the way we're going to do it is you're going to be given the equation for a function of two variables, say z equals fxy. And as you'll recall, the graph of that is a surface. So I'll just do sort of a capping surface here like this. Okay, here's a surface. And I can pick a point on that surface, you know, my favorite point anywhere on there. And I don't know, let's use green because it's St. Patrick's Day right there. And instead of a tangent line, I'm going to have a tangent plane. Can you picture that? A tangent plane at that point? I hope so, because that's what we're going to do today. And I hope you recall that when you have to go find the equation of a tangent plane, there were two pieces of information that you needed to have in order to come up with the equation for a tangent plane. So does anybody remember the two things that you need to get your tangent plane equation going? We'll just make a little list here.
A point on the plane.
Good. Point on the plane. Perfect. And hey, good news, they'll always give you that because it's the same as the point that's on the surface, since the tangent plane is tangent to that point. What's the second thing you need? Anybody remember? You need two things. I know it was some time ago when we did equations for planes. Does anybody remember the second thing you need for the equation for a plane?
Wasn't it a normal vector?
Yes, a vector that's normal, we'll call it n, a vector normal to the surface, also known, you can say orthogonal, normal to the plane. Does everybody remember this? I know you guys are real quiet today, but you need to remember this right here, because if you don't, then today's lecture is going to be not very fun, and you know, that kind of thing. So I'm hoping it's fun. So I hope you keep your eyeballs on how the heck do we get the vector normal to the plane. So keep asking yourself that question as we begin today's lecture. Okay, how do you get that vector normal to the plane? This pink vector here. Okay. Oops, wrong place to go. All right. So we're going to find equations of tangent planes today and also normal lines. We'll talk about that in a little bit. And we're going to look at the angle of inclination of a plane in space. And we're also going to once again compare the gradients little del f, which is a two-dimensional vector, and big del f, which is a three-dimensional vector. And hopefully you don't get tricked between one or the other on the quiz or a midterm, because I will try to trick you. We'll see what happens. Okay, first up, what do we know so far? So far, we've represented surfaces in space by equations of this form, at z equals fxy. And this is known as explicit form. This is known as explicit form, where you get z on one side and all the X's and Y's and constants on the other side. But we're going to look at a more general representation today. The more general representation that we're going to try to look at is where we look at a function of 3 variables. So we'll call it big F, uppercase F. And we're going to set it equal to 0, because remember, a function of 3 variables you cannot graph because you need 4 dimensions, which we're not going to go there. But when you set it equal to 0, that's like finding a level surface for the function of 3 variables. So this is understood to be a level surface where the constant is 0 of the function big F, where the constant, usually when we find level curves or level surfaces, I've instructed you to, step 1, set the function equal to a constant. Here, the constant is a special constant at 0. So where the constant is 0. So that's the general representation of a surface we're going to look at, where it's understood to be a level surface. So what are we going to have to do to get this more general representation? By the way, this is known as the implicit form. So what you're going to do is when somebody gives you this little z equals little fxy, you're going to rearrange it. You're going to get everything on one side and 0 on the other. And it doesn't matter which side, okay? Just left side, right side. Later on, it is going to matter which side. Like, this stuff isn't going away. So what I usually do is I just subtract z from both sides, really easy to do, so that on the left side, I get the 0, and on the right, I have some function of x and y. So I've got x's and y's running all over the place with some numbers, minus z. So then what? So this guy right here has x's, y's, and a single z in it. I know it's kind of ridiculous. Well, we just have one z in there. I know, but we're going to rename him big F. So big F is going to be this function of x, y, and z, where there's only a single z in there. I know it's kind of ridiculous. And we're setting it equal to 0 because we just rearranged the original explicit equation. So then this surface is understood to be the level surface for F. Okay, so let's just do a quick example, just as a reminder example from a previous section. Describe the level surface given by big F x, y, z equals 0 for this function. This is just review right here. This is a review problem. So you know the drill. Step 1 is you set your function of 3 variables equal to a constant, but they want the constant to be 0. Okay, so here we're just going to set x squared plus y squared plus c squared minus 4 equal to 0. When I rearrange this equation, does anybody recognize this as something familiar to you?
Kind of.
What is this equation of? It's a surface, but it's a real special kind of surface. I think we
Square plus
studied
b
it in the
squared
first.
equals c squared.
A sphere?
A sphere. A sphere centered at the origin of radius what?
2.
Yep. So hopefully you recognize this equation. This is one of the baby equations we studied way back in week 1 when we did some basic stuff. And if you forgot, don't worry. We're going to remind you over and over again. Practice makes perfect. So now let's do a definition of a tangent line to a surface, and then pretty soon we're going to derive the definition for the tangent plane to the surface. So if you've got a point, we're going to call it P naught, P subscript 0, P naught, with coordinates x naught, y naught, z naught. Let's say it's on your surface, big S. And let's assume that these partials, fx, fy, fz, are not all equal to 0. A tangent line to the surface at that point is a tangent line to any curve that lies on that surface and contains that point. So here's your capping surface again, say that's supposed to be a capping surface, you know, and let's say its equation is given to you by fxyz equals 0. If you pick a point P naught on that surface, how about right there? There's a point, we'll call it P naught. If I draw any curve on the surface, I'll just draw a baby curve. Here's a curve, C. We'll call that curve C. And if I sketch a tangent line to the point P naught and to the surface like that, I'll get that. So there's the tangent line. Okay. So you've got your C, you got your curve, and we're going to represent the curve using parametric equations. So you know the drill. You know, you've got, say, x is equal to some, say, x of t, y is equal to y of t, and z is equal to z of t. So, you know, curves you can represent parametrically, right? Or by a vector valued function. We're not doing a line parametric equations here. We're doing some weird curvy curve, which is like right here, this curve. Okay, now, if you did want to write it as a vector valued function, you should know that you just take the parametric equations and use them as components inside your vector valued function. So either way, this represents the curve C, and then this is another way to represent your curve C. Either way, fine. Now, since the curve is on the surface S, and the surface is given by this more general representation, the level surface representation, then you can plug in the x of t, the y of t, and the z of t in place of x, y, z, and it better satisfy your function because it's on the surface. So this has to be true right here. I'll put a star by it. That has to be true. Got it. Now, if f is differentiable and x prime and y prime and z prime all exist, you can use the chain rule. So why do we want to use the chain rule? Well, we just got done with a quiz on the chain rule. So let me just draw one of these tree diagrams because I love these tree diagrams. Here's f. It's a function of x, y, and z. But x, y, and z are all functions of t, like that. So t is driving the bus. So how would you get df dt? So f prime of t, which we could write df dt, you're going to take the derivative of this, and you know, using this tree diagram here, you're first going to go df dx times dx dt, and then go down this branch, partial of f with respect to y times dy dt, plus the partial of f with respect to z times dz dt. So you're going to write all that out. So that's just your chain rule in action. And anytime you're going to use a chain rule, I require that you write it out. So if you look over your quiz you took for me the other day involving the chain rule, I may have taken a point or two off if you neglected to put this form. Now what? Well, if you're looking at this equation here, the left-hand side's derivative, which is df dt, had better equal the right-hand side's derivative. Well, the derivative of 0, no matter what, is 0. Okay, so great. Now what? What are we saying? We're saying the derivative of this function f is, with respect to time, goes to 0. But I want you to notice this right here. Doesn't this look like a dot product? Has that flavor to it. Something times something plus something times something else plus something times something else. So it looks like a dot product. In fact, it is. It's the dot product between the vector del f, which is the gradient of big F, and r prime, the tangent vector to the curve. So when you have a dot product that equals 0, what can you say about those two vectors? You learned this back in week 2.
They're orthogonal.
Yeah. So the gradient of f is orthogonal to every tangent vector of every curve on S that passes through that point, P naught. Cool. That's awesome. So all the tangent lines at P naught lie in a plane that is normal to the gradient of big F at the point P naught. Now, if you don't believe me, I want to show you that these tangent lines all form a bed, that the tangent plane contains all those tangent lines. So what the heck did I just say? Let's go back to the previous page with a little diagram on it so you can see what I'm talking about. It's not that hard to get what we're saying here. So go back to this diagram. So I drew a curve that was red. I could draw another curve, I'll use pink, that also goes through the point P on the surface. And I could draw another tangent line to that that goes through. There's another tangent line. Okay, fine. Then what? I can draw another curve that lives on the surface that passes through the point P, like right there. And so then I can draw like another tangent line. Okay, like that. So pretty soon I'm going to get all these curves on the surface that pass through the point, and then I get all these tangent lines. So I'll just kind of draw a whole bunch of tangent lines that pass through the point P. Just going to get a whole bunch here. So what I'm claiming is all these tangent lines are contained in a tangent plane. The tangent plane contains all of those tangent lines. And we just got done saying that the gradient of big F is always going to be orthogonal to any of the velocity vectors, if you will, or R prime, which means only one thing that we just saw, that all of those tangent vectors are orthogonal to the gradient of big F. So why is that awesome? Because when I asked you to keep your eye open for the normal vector to the plane in order for us to come up with the equation of the tangent plane, we just found it. We just answered the question. It's the gradient of big F. So now you're ready for the definition of a tangent plane. And while we're at it, we're going to define what the heck a normal line is also. Very easy if you understand the tangent plane. So we've got big F, it's differentiable, and keep in mind that big F is part of this general representation of your surface, where big F is set equal to 0. Let's say it's differentiable at this point that's on the surface, and the gradient is non-zero vector, because that would be bad. Then the plane through the point is going to be normal to your gradient, and it's called the tangent plane to the surface S at the point P naught. There it is. And then the line through P naught that has the direction of the gradient is called the normal line to the surface S at the point P naught. I'll draw a picture of the normal line. First, write this down, that the line through that P naught and having the direction of the gradient is called the normal line to the surface at the point P naught. So where's the normal line? We weren't discussing lines. We were discussing tangent lines, but that's not the normal line. That's different. So if we go back to my little diagram here, that's kind of a mess right now. We've got the tangent plane to the surface. Okay, fine. And then this gradient here is going to be the direction vector for the normal line to the plane. So here's the normal line to the plane. It pierces the plane, makes a 90-degree angle with it. It's orthogonal. And it's normal to the surface. And you just use the gradient del big F for your direction vector. So you can easily get the parametric equations for that normal line, which you're going to do on the quiz this week. I'm going to ask you for equations of tangent planes to the surfaces and normal lines to the surfaces, both. And folks, this is easy. Like, this is going to be one of the easiest topics you learn in chapter 15, because you already know about how to get equations for planes. You already know about how to get parametric equations of lines. It just ties everything together for us. It's wonderful. Okay, so now let's do a GPA, a general person's agreement. That would be Dr. Vallone. He would always say that, of blessed memory. So we'll always assume that the gradient is not the 0 vector, because then we won't be able to get these equations for planes or lines. Okay, now let's get the equation for the tangent plane. So just a little recall now. Equation for a plane that contains a point and has a normal vector n is represented by this standard equation for a plane. So here's the standard equation for a plane. And for some reason, some of you totally ignore me when I say standard equation for a plane. How come I know this? Because when I was grading quizzes a month ago, some of you never even went through this intermediate step of standard equation for a plane because you were viewing the Briggs view and example, which is sad because I give you all my gold and I expect you to use it. So if I ask you for the standard equation for a plane, please know what it is. It's this. And I may do that on an exam.
Oh,
I think we lost her.
Yeah, we lost her.
yeah.
Nah, take it. Oh, hey, we're still recording.
Yes.
No.
Yeah, we like lost her.
She'll be back.
Okay, sorry about that. I don't know why my Surface Pro died, but are you guys still there?
Yeah.
Yeah, we can hear you.
Yes.
Sorry about that. Everything just went dark. Like that was it. Okay, so back to standard equation for a plane. Please know what it looks like. That's it. And I used it for the derivation when we did planes like a month or so ago. Okay, so now here's the official equation for the tangent plane. So what am I saying? The ABC, that is what we're going to use del F evaluated at the point P naught. And so the components of your gradient are going to be the values of A, B, and C. So you're going to go like this. Your A is going to be your Fx evaluated at the point X naught, Y naught, Z naught. So it better be a pure number. If I see X's and Y's squared and all this other nonsense in your equation, your gradient at the point, I'm not going to give you any credit. I'm telling you right now. Like that's a mess. Your plane equation is only allowed to have X to the 1 power, Y to the 1 power, and Z to the 1 power. So if I see other powers and other nonsense with X's, Y's, and Z's, sine X or blah, 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 you miss the boat. That's going to be sad. Okay, and then the other pure number, you're going to take your partial with respect to Y of your big F and evaluate it at the points. You're going to get a constant times Y minus Y naught plus the partial with respect to Z. Can you guys hear me okay? Because now my internet's unstable.
Yeah, we can still hear you.
I'm getting a message here. It's always something. Monday I had to go to school to Zoom for you guys because my internet was being worked on, and they supposedly did something amazing to it so that it's awesome now, and I found it to be worse. I don't understand. Okay. Okay, now let's do the parametric equations for the normal line. I don't know what to do to make this internet better. Huh. No, don't know. Okay, so what about the parametric equations for your normal line? Well, you're going to use the gradient again as the direction vector for your line. So you're going to have your parametric equations here, X, Y, and Z, get it all set up here. And you know a point on the line, it's just going to be that point with coordinates X naught, Y naught, Z naught. And then your direction vector, whose components are going to be the coefficients for your T, your parameter, you're just going to go, okay, Fx evaluated at the point, so it better be a nice number, times T plus the partial with respect to Y evaluated at the point times T. And then over here, the last parametric equation, has the partial with respect to z evaluated at your point times t. Okay, so now let's do an example. Can you guys see that error message on my screen that says my internet's unstable? Do you see it?
No.
No.
No,
Okay, only I see it. It's like it's not going away. It's like stuck there.
We see your share screen, but we lost visual on you.
Yeah, I get it. Weird. Okay. Oh, now it went away. Okay, so here's a typical problem that you'll get on this week's quiz. Okay, except maybe the numbers are a little bit different. So I'm giving it away. It's easy. Here's some surface. Please keep in mind the way they're giving you the surface is implicit. They're not saying z equals a function of x and y. You could, if you really worked hard, isolate the z on one side and get the rest of the junk on the other, but it would take a lot of work. Like, good luck. So best not to try to do that. Instead, though, I do want to see step one. I want to see you get that general representation, because if you don't, you're going to blow it. You want everything on one side and 0 on the other. That's your step one. It doesn't matter which side, so as long as one side. So I'm going to just get everything on the left. And to do that, I'll simply subtract 4 from both sides and subtract y squared z from both sides. Great. Now what? This on the left-hand side is your big F, which is a function of 3 variables, x, y, and z. Okay? And they want you to just find a normal vector to the surface. Well, a normal vector, folks, is going to be your gradient evaluated at the point -1, 1, -1. Because we went over when we were doing gradients the last lecture that the gradient is normal to your surface, your level surfaces. That's a theorem. Know that. So if we could just get the gradient and then evaluate it at this point, we'll have the answer for letter A. Done. So the normal vector is the gradient of f, which we use this upside down triangle, and that we call that del f, and it's a vector, and it's going to contain the partials of this function that we just got everything on one side and 0 on the other. Can you guys hear me okay?
Yeah, we can hear you.
Okay.
Yeah.
I'm just I don't know what's going on here. Very strange. Okay. So as usual, I never give myself enough room to do a problem. Why is that? Okay. So I'll just drop it down here. So del F for us is going to be, let's go ahead and take the partial with respect to x of this big old polynomial here. I get 2xy cubed plus 2z cubed. I think that's it for the partial with respect to x. Okay, comma. Now let's take the partial with respect to y. I get 3x squared y squared for the first term. And then the second term goes to 0. And then the last term minus 2yz. Okay, there's the partial with respect to y. And then finally, the partial with respect to z, I get, the first term goes to 0. Second term, I get 6xz squared minus y squared. Okay, there is the gradient. Fantastic. Now what? Well, the normal vector to the surface at the point -1, 1, -1, you're just going to substitute -1, 1, -1 into this big mess. And I'm just going to kind of go quickly here. I end up getting, after I do all the arithmetic, I get like -2 plus -2. Then I get 3 plus 2. And then I get -6 minus 1. I get -4, 5, and -7. Those are the components. And that is it. We're done with letter A. That's a normal vector to the surface. So what does it mean, like visually speaking? Because I get students who they just don't get this. Here is some, say, capping surface. Let's say that right here is the point P naught. Okay. If I told you to graph this del F, what would you do? Well, you first could graph it in standard position if you like, and then move it up and translate it so that it's sticking out of the point P naught. And I claim it's going to be this vector that is orthogonal to the surface. Right there, it's sticking out. It's a 3D vector. Does that make sense, folks? Are you still there?
Yes.
Yeah.
Okay.
Uh-oh.
Yeah, my Zoom is dead.
A lot of technical issues today, huh?
Yeah, I'm not having much luck with the internet today. I may have to, I might have to reboot my system. So don't be alarmed if I just close it out altogether, because this is, I can't even get my Zoom to respond right now. It's like dead. I'm surprised you guys can hear me, to be honest, because this is, I keep getting an error message. Internet's unstable. Zoom is not responding. It's just a mess. Wow. Interesting. Can't do anything. Wow.
One of the first, actually. I don't think we've ever had like a problem with Zoom until right now.
Yeah, after my internet supposedly was worked on. Yeah. Okay. Well, I'm just going to keep going, and then if we die, we die. Okay, so letter B is just a fallout. It's a natural fallout. Now that you've got that normal vector, yay, let's go ahead and get the equation of the tangent plane. Fine. So then what? Well, -4, 5, and -7, this is the normal vector to the plane. So you're just going to use that to help you get the equation of the tangent plane. Fantastic. So there's really not a whole lot of thinking here. So I'm going to have -4 parentheses x minus a -1 is x plus 1, like so. And then plus 5 times the quantity y minus 1 minus 7 times the quantity z minus a -1 is z plus 1 equals 0. That's the standard equation. And usually they like the general equation. So you usually you distribute and you combine like terms and you rewrite it so that it's general form. So my general form looks like this. I'll just leave it like that. So this is the general form for the equation of a plane. Okay. And then finally, go write the parametric equations for the normal line to the surface. And that's easy. You get your parametric equations here. They gave you the point. So I'm just going to put those coordinates in. And then -4t plus 5t minus 7t. Boom, done. Okay, and then a couple other weird questions. What's the gradient del F to this level surface? Well, we already got the answer in part A. So what am I saying? We already got it. It's -4, or the gradient to the level surface is just del F, which I don't feel like writing all around again because we just did it. So that you can use that to find a normal vector to any point on your surface. Okay, now consider this level surface. Oh boy. No, I don't want to Skype. I don't know how I got in here. Okay, so what is the value for the constant c at the point 3, 2, 1? So what you're going to do here is you're going to take your fxyz, which is x squared y cubed plus 2xz cubed minus 4 minus y squared z equals 0. But if you want to set it to c instead, we'll go like that. And then you'll substitute this point in place of x, y, and z respectively. So you're going to go, okay, 3 squared, 2 cubed plus 2 times 3 times 1 cubed minus 4 minus 2 squared times 1 equals some constant, and then add up all this together. I get 72. And we're done. So that would be the value of the constant for a different level surface. Instead of the constant being 0, we're saying, okay, we want the constant to be something else. Okay. So any questions on this so far?
Uh-oh. I think we actually lost her again.
She's probably resetting it.
Well, I still have problems with this. It's still not working. Wow.
Well, we can see you again.
Yeah, that's great. Okay, I'm just going to keep going and pretend that this day is not happening. Okay. All right, we're going to do a different problem. It's going to have a different flavor. So look to what is different about this problem compared to the previous problem. And the reason why is this is where I get students. This is where they fall into my pit of despair, that I set the trap for them. And they think, oh yeah, I know this stuff. This is easy peasy. I'm done here. I'm going to fall asleep now. Okay, at your peril. Because this is where I'm going to catch you. And I'll find out that you really didn't get it. Okay? So what's the different flavor? Here they're giving you a surface fxy equals 16 minus 2x squared minus y squared. What could possibly go wrong? A lot. Okay? So let's use this to answer the following questions. So as this problem progresses, what I want you to notice is try to see if you can't make connections between the last lecture we had on Monday and what's going on today, as well as the new material I've covered today. Does any of all this relate in some way, or is it all completely distinct and separate? And so in my opinion, a good student does pretty well, and they kind of, do an okay job of, going through the motions. A great student is one that can make these connections of all the concepts, that really has an underlying understanding of what's happening here, not just like, yeah, I know how to do those kind of problems, or I can do that kind of problem, but really knows what's going on, because then they can handle anything that gets thrown at them for a quiz or exam. So take a look here. We're going to find little del f, little del f, little. So you have to be careful, because this is a two-dimensional vector, not three, that contains the first partials of this function f. Okay, fine. So it looks like this is a pretty easy function to find the partials. So I'm just going to go ahead and get it, and I'm done with part A. Fine. Move on. In letter B, we're going to use the gradient of little f to help you find the directional derivative for the function at the point P with coordinates 1, -2, in the direction of the point Q, -3, 4. And we did a problem just like this last time when we were looking at directional derivatives. Okay? So if you recall, you have to first get a vector that's pointing you in the direction that you want to find the directional derivative, and then you have to unitize it. And if you don't unitize it, you'll get 0 points. Yeah. And that's what happens on the final every time. Every time I get students who like lose out almost like a full letter grade, because I make this worth a lot of points. And it's not that hard if you just follow directions. Okay, so I get that vector, but then I have to unitize it. So let's go ahead and find the magnitude of PQ. So what's the square root of 4 squared plus 6 squared? Ooh, I don't know. What the heck is the square root of 16 plus 36? I get square root of 52. Please, if you can, simplify all your radicals. And it turns out that 52 can be factored as 4 times 13, 52 cards in a deck, divisible by 4 suits. And so this can simplify a little bit. So then your unit vector can be easily formed. And then I'll reduce to lowest terms, and I'll get -2 over square root of 13. And I'll get 3 over square root of 13. Fantastic. Now what? Well, let's evaluate our gradient at the point P. And we already got the gradient. That's little f that I'm doing, little del f. That's up here. This is little del f. So we're going to evaluate that guy at the point 1, -2. So I'm just going to substitute the point with coordinates 1, -2 into that guy. And then I get -4, 4. So then what? So then you can do your directional derivative. And the notation is big D subscript u, that's in the direction of the unit vector. F, evaluated at the point P, is you're going to take the dot product between the two vectors. So I'm going to take the dot product between my gradient and my unit vector. And I'm going to get a weird number. Huh. So I'm going to get 8 over square root of 13 plus 12 over square root of 13, which is 20 over square root of 13. Ooh, that's a weird number. And we're done with letter B. That is the directional derivative. And please keep in mind that directional derivatives, because they're slopes, the result is a scalar, not a vector. I get students who give me a vector when, they'll actually do something weird like this. So please don't write this down. They'll go, oh yeah, the vector 8 square root of 13 with other, oh, there's my directional derivative. Yeah, that's right. That's the ticket. Oh, no, 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 no. Directional derivatives are not vectors, okay? Gradients are vectors. That's true. Okay, now letter C. This is where it gets fun. This is where I find out who knows their stuff and who thinks they know their stuff. So we're going to find a normal vector to the surface. So should I use little del f?
No.
No, why not?
3 points.
Because little del f is a two-dimensional vector that lives in the xy plane. It is not a three-dimensional vector. So a normal vector to the surface would obviously not be flat there in the xy plane. So no, you don't want to use little del f. Well, what the heck are we going to have to do? We're going to have to do some work. So watch closely so you can make this connection. You're first going to replace the fxy with z, because that's basically what it is. So when you do that, let me just write it down. So I have z equals 16 minus 2x squared minus y squared. Then you need to write this equation in the general representation for a surface, where you have big F, which is a function of 3 variables, equal to 0. Get everything on one side and 0 on the other. And for now, it doesn't matter which side of the equation you get everything on and which side has the 0. Later on, it is going to matter. I'm just pointing that out for later. So how about if I just subtract z from both sides? So when I do that and then rewrite this, oops, minus z. So this mess on the left-hand side that has x's and y's and a z in there, that is a function of 3 variables, x, y, z. So now we have it. Now, the normal vector that you're going to get is del big F, x, y, z, which is a vector with the partials of big F, not little f, because you want a 3D vector. So we get the partials here of this function of 3 variables, and the fx partial with respect to x is negative 4x, and then fy is negative 2y, and z is just negative 1. And they want us to give the normal vector at the given point 1, negative 2, 10. No problem. I'll just evaluate this big gradient at the point 1, negative 2, 10 just by substituting. So that's a negative 2. Watch out for my negatives there. Negative 2 and then negative 1. And then I get the vector, what the vector do I get? A negative 4, positive 4, negative 1. That is a vector that's normal to your surface. Now, when I say normal, let me just draw again at the risk of being redundant. Here's your capping surface, whatever that surface is. So that's represented now by big fxyz equals 0. And you find your point, which had the coordinates 1, negative 2, 10. I don't know. Let's say it's way over here. Fine. Then this vector that we just found is normal to that point. That's this vector right here. That's your gradient, big del F. That's him, or to draw him up. The little del F would just be way down here in the XY plane. That's definitely not normal or orthogonal to your surface. I hope you can appreciate that. The big difference between these two creatures here. So there's the normal vector to the surface. Fine. Now, letter D, let's describe the level surfaces for this function. So if you set, or the level curves rather, level curves is where you set little f equal to a constant. So 16 minus 2x squared minus y squared equals some constant. And if you rearrange this equation, you know, where you get the x squared y squared on one side and the other junk on the other, I get something like this. What does this equation remind you of? I'll give you some choices. Circles, ellipses, hyperbolas, or parabolas. What does this remind you of?
Ellipsis?
Ellipse.
Yep. So the level curves for this function will be ellipses. Okay, fine. Now let's finish this out. What's the equation for the tangent plane? Well, you're going to use this normal vector that we just found for the normal vector to the plane. So setting up the standard equation, because I always do that first, so I'll have negative 4x minus 1 plus 4y minus a minus 2, but that's y plus 2, then plus negative 1 here times the quantity z minus 10. That equals 0. That's the standard equation. And if I distribute and multiply things out, collect like terms, add it all together, make it look pretty, nope, I don't want to do a zooming another meeting. Nope, I don't want to do that either. You'll get the general form for your equation of your tangent plane. This is the general form. I initially got negative 4x plus 4y minus z equals negative 22. But when you have that many negatives in it, it doesn't look very pretty. So I just multiplied both sides by negative 1. And this looks a little nicer. For those of you who are like wondering how I got this for my final answer. And then finally get the, well, second to the finally, get parametric equations for the normal line. So you know the drill. The big del F is your direction vector. So I'll get what, minus 4t plus 4t minus t for the coefficients on my parameters. I'm done. Here's the parametric equations for the normal line. Cool beans, done. Almost done with the whole problem. Now this is the key right here. Do you understand this? This could be like a true false question, or I could formulate it into some conceptual true false. See if you're understanding. So which vector, little del f, that's the vector we found initially in part A, or big del f that you found in part C, would give, if they asked you for it, the direction of the maximum rate of increase on the surface at the point 1, negative 2, 10.
Isn't it big del F?
You'd think, wouldn't you? But
It's little, yeah, it's the little one.
it's little del f. And let's go over why, because I know it's like, well, wait a minute, I'm on the surface and I want to get the direction of maximum rate of increase. Well, we did this on Monday. Monday, one of the big old theorems about gradients, and that was two-dimensional gradients, little del f, is little del f, the 2D vector, points you in the direction of maximum rate of increase. But wait a minute, they're saying on the surface, yes. Well, how does that make sense? I'll tell you how it makes sense. So if you were on the surface, let me just use the diagram I already have. So let's say you're right here at this point. This is you standing right here. Hey, and you got your ski poles. Maybe you got your skis. Okay. And you want to, let's say you want it, well, maybe you don't want to ski because downhill is the opposite of del F. What you're doing here, your little del F here is, remember, it's a 2D vector. So if you can imagine, even though you're standing up here on the 3D surface, you hold out your hand flat, okay? And I don't know if you can see me in my video here. You hold your hand flat and put a compass here, and the compass is flat in your hand. So you can think of it as being a 2D vector because it's, you know, flat 2D in your hand. it's pointing you in the direction of the maximum slope of the surface. But again, well, the surface is 3D. I know. This is what's so amazing, is that the two-dimensional little del f vector, the little gradient, points you in the direction of maximum slope at like a compass, even though you're in 3D. And see, this is the other amazing thing, that after all of today's discussion, letter B should also floor you. Like when we found this directional derivative here, which is the slope of the 3D surface, we didn't use the three-dimensional big del f gradient. No, no, no. We used little del f, the two-dimensional gradient, to get the slope of the 3D surface. That's like, wow. You should all be saying wow right now. Wow. Okay, so the direction that's going to point us in the direction of maximum rate of increase would be little del f at the point 1, -2. And if you substitute the point 1, -2 into your little del f that we got from part A, you would get this vector, and that would point you in which direction to go. Okay. Questions? So to recap this problem, and why does it trick students? Because the fxy, students forget that they can replace little fxy with z. Really? I'm allowed to do that? Sure. Remember in your algebra class when you were given, say, y equals f of x? You know, like like you were given, say, f of x is equal to x squared, just as a cheesy example. Didn't you remember that it was okay to rewrite it as y equals x squared? True, right? True. So what's also true, now that you're here in Calc 3, welcome. Anytime you're given little f of xy, you're allowed to replace the fxy with z. And you need to do that because when they're going to ask you for the normal vector to the surface or the tangent plane equation for the surface or a normal line to the surface, you're going to have to rearrange that whole equation into this more general format for a surface equation. Everything on one side and 0 on the other, so that you can get the big 3D gradient, big del f, which is different from little del f, which you can use for your directional derivative and to point you in the direction of maximum increase. Okay, we're not done, so let's keep going. How do you get the angle of inclination of a tangent plane? Okay, so let's just do a little recalling. So recall from about a month ago that when you had two planes and I asked you to find the angle between two planes, just regular two planes, not necessarily tangent planes. So there was an angle here, theta. You basically found the angle between the normal vectors instead, is what you ended up doing with the formula. So you had, like here, you had, say, n1, and then this plane had a normal vector n2, and the cosine of the angle between them, you use your knowledge of that theorem, but we wanted to guarantee that the angle was acute, so you put absolute value bars here around the numerator to ensure that you get a positive cosine. That way you'll get an angle that's between 0 and 90. Okay, fine. So how do we use this formula from like a month ago to get the angle of inclination of a tangent plane? And what do they even mean, angle of inclination of a tangent plane? So once again, let's say here's your capping surface like this, and let's say here's your point P, and let's say you actually get a tangent plane to that point. So I'm going to draw a tangent plane to that point, yeah, like that. So if I could extend that plane all the way down, because remember, it goes off in infinity directions, what angle is that plane making with the flat XY plane here? With the horizontal, essentially. Okay, so what angle is it making with the XY plane? That's known as the angle of inclination, right there. Okay, now we also still want it to be an acute angle. And then what's an obvious normal vector for the XY plane? We're the obvious normal vector k hat, which has component 0, 0, 1. Because it's obviously orthogonal to the XY plane. So we can use that guy for his normal vector. So now the cosine of the angle between your tangent plane and the horizontal is going to be the absolute value of del big F dot product to the standard unit vector K, and you'll divide by the product of the magnitudes. But good news, what's the magnitude of K?
1.
So this really just ends up being the absolute value of your big del F 3D gradient with K hat and divided by the magnitude of big del F. Sorry, this should be big del F here. Big del F. Okay. So now let's do one problem involving angle of inclination. Okay, fine. So the example 2 that we did way back, not this last example, but example 2, way back here, right here. Let's find the angle of inclination of the tangent plane that we found here in part B with the horizontal. So here was the general form for that tangent plane. So we know what the normal vector components are, -4, 5, and 7, because those were the components of the big old gradient. So we'll just use that so we don't have to do so much hard work. So we already got big del F evaluated at the point -1, 1, -1 was this vector, -4, 5, -7. We did that already. So cos of the angle, so the angle is the angle with the horizontal. So you're going to take absolute value of this dot product, this gradient dot product with 0, 0, 1. That should be pretty easy. And then you'll divide by the magnitude of this gradient. Okay, fine. So the numerator is simply going to be absolute value of -7, which is 7. And here we have 16 plus 25 plus 49. I get square root of 90. And you can simplify that a little bit, but we really don't care too much because we're really taking cos inverse of 7 over square root of 90. And in degrees, I get 42.45 degrees. And that's the angle of inclination we're making there. Okay, that's kind of cool because we're using some previous knowledge from like 2 months ago. Time is just flying. Okay. Questions so far? I got a question. Why is my internet so wonky? That's what I want to know. Okay. So let's just revisit this comparing the gradients again so you're clear. Little del F and big del F. So if little f is differentiable, then the gradient of little f is orthogonal to the level curves of f. But big del F, big gradient is normal, and normal and orthogonal a lot of times are used interchangeably, to level surfaces. That's level surfaces. To the level surface, I should say, through that point P naught. So little del F is a little 2D vector that's normal orthogonal to level curves. The big del F gradient is orthogonal or normal to level surfaces. Okay, fine. So just a reminder, little del F is a 2-dimensional vector, so it's a vector in the plane, whereas big del F is a vector in space. So don't lose sight of that. Okay. So I think I'm going to do one more problem and then I'll call it. And this is going to be on the quiz. Okay. Yes. It's going to be on the quiz. I like to put it on exams also. Why? It's a classic. Like every single calculus book you see is going to do this problem. So, so let me remind you of what this problem is like after I read it, because I claim you've already done a problem like this. Good news. You've already seen this. Really? I don't remember. It looks terrible. No, you've seen it. So first let's walk through it and then I'll tell you that you really have done this already. Okay, I know it may not seem like it, but you did. Okay, so this is a classic. It's where you're given two surfaces, okay? And when these two surfaces intersect, they create a curve, like a trace, if you will, of intersection. And we're going to pick a point that's at the intersection of these two surfaces. And we're going to draw a tangent line to that curve. And then we're going to give the parametric equations for that tangent line. Holy crap. Are you kidding me? No, I'm not. So like the point 013 is probably going to be right about there. This right here is the egg-shaped looking thing. That's the yellow, the ellipsoid. And then this guy right here is the paraboloid. Okay, so that's the green guy. So when the egg and the paraboloid intersect, you can think of, you're getting like this elliptical curve here. And so, and here's the point they're talking about. And if I draw a tangent line to that point, they want the parametric equations for that tangent line. Oh my God, are you kidding me? No, I'm not. So I claim you've already done this problem, really, in a similar way with two surfaces. So I want you to recall about a month ago that when we were studying planes and lines in like a couple chapters ago, when I gave you two planes, their curve of intersection, if you will, is a straight line. So their intersection curve was a straight line, if you recall. And I asked you to give me the parametric equations for that straight line. And if you forgot how to do this, let's review how we did it. So, because it's going to be similar strategy to do this slightly harder problem, but it's along the same lines. You're going to get the normal vector to both of these tangent planes, which is essentially its gradient. Okay, so you're going to get like in normal 1, normal 2, and then the so they're normal to both those planes, and then the direction vector for this line was given by n1 cross product n2. Does anybody remember this?
Yes.
Yes.
That's similar to what we're going to do here. Really? I don't see it. Well, here's the thing is here at this point, if you got the paraboloid's del F, so we'll call this guy big F once we get him on one side and everything on another G, big del F. And then the egg has his gradient to that point. Yellow doesn't make a good thing, so I'll do orange. So his gradient, you know, might be more like that. I don't know, that's like big del G. And I claim that the cross product of those two vectors is going to give an orthogonal vector to the vectors, of course. And it's going to be a direction vector, this blue vector here, for the line that's tangent to the curve of intersection. Boom. That's basically what we're doing and what we're saying. Really? Yeah. Not that bad. So first up, we have to do our step 1, which is a rewrite. And I want to see this rewrite as your step 1 and your quizzes, your handwritten work. If I don't see that and you skip a step and you go, well, I did it in my head, I'm not going to be okay. I want you to rewrite both equations where everything is on one side and 0 is on the other. So you understand that that's like an important thing. So you may even still get the whole problem right without doing this, but without acknowledging that you need everything on one side and 0 on the other as your general representation, you're not getting this. Okay. All right. So with the paraboloid, I get everything on one side, 0 on the other, and then we'll call this big old function of 3 variables g of x, y, z. Fine. Okay, so now we're going to go get the gradients. So we're going to get del big F, and we'll get del big G. So let's do this in turn. So this is a vector containing the 3 partials. So I'm just going to do this real quick. When I take the partial with respect to x, I get 2x. With respect to y, 4y. And with respect to z, 4z. Okay, that look good? When I get big del G, which is another vector containing the partials of this function, I get for the partial with respect to x, 2x, with respect to y, 2y, and with respect to z, 1. Okay, fine. And now, I mean, I could take the cross product with all the x's, y's, and z's, but I don't like that kind of pain. I already know that I need to get these gradients evaluated at the point P. So let's get some constant vectors. So let's get del F evaluated at the point P, which is, oops, I'm using this notation. Boy, I'm really blowing it. Sorry, trying to write too fast. Coordinates 0, 1, 3, just plug them all in and I get 0, 4, 12. Okay, and then when I do the same thing with the other gradient, plug in the point 0, 1, 3, I get the vector 0, 2, 1. Fine. So far, so good. Now what? It's cross product time, people. You know, don't ever forget your cross product because that's just going to keep coming back. It never goes away. Just when you thought it was safe to ignore cross product. Okay, so here we go. We're going to go del F cross del G. And you know me, I like to see correct 3 by 3 determinant notation. Some of you still don't get this. I want not brackets, but straight lines here. This is how you represent a determinant of a matrix. You use straight lines, not brackets. And then the I hat, J hat, K hat is the top row. The components of that first vector del F go in the second row, and the components of the other vector go in the last row. And then, you know, 2 by 2 I hat minus 2 by 2 J hat plus 2 by 2 K hat. And then when I just copy all these down for 12, 2, 1, this one's going to have 0, 12, 0, 1. This one's going to have 0, 4, 0, 2. And here I'm going to go, oh, 4 minus 24 I hat. This is going to be 0 J hat, 0 K hat. Ooh, that's kind of nice. So we get the vector negative 20, 0, 0. Wow, that's amazing. So then the parametric equations for the tangent line to the curve of intersection, we're almost done. You got everything you need. You got a direction vector, which is negative 20, 0, 0, and you've got the point. They told you it was 0, 1, 3. So your parametric equations are 0, I'm not going to bother writing, minus 20t, and then 1 plus 0t, and then 3 plus 0t, and you're done. There's your parametric equations for that line. Pretty cool, huh? So you've done something similar already, but the two surfaces were just planes, so it wasn't as, seems not as tricky. But this is really the same thing. You're just getting the normal vectors to the plane basically are the gradients for the planes. But now when you kick it up another level and you've got surfaces, you need to get normal vectors to the surfaces. Those are the gradients. Exciting stuff. I love this stuff, people. Look at that. See, nice picture. Okay, I'm going to stop the sharing. We're done.